I guess we can get started now. First thing, announcements. Tomorrow from 7 to 9, Aaron Yu will be giving a talk at, that's the OS lab, right? Yeah, Aaron Yu will be giving a talk at the OS lab. Aaron Yu is a cyber alum. He's now a software engineer at Apple. Very cool person. You should come check it out if you have the time. It'll be in Bolter 4760. Also this, why can I hear myself again?
You can ignore that.
This Saturday at 11 a.m. Very cool. Live Overflow, who is like a very famous cybersecurity YouTuber. He has like, I think over 300,000 subscribers. 800,000. Oh, he grew a lot.
Yeah.
So he has over 800,000 subscribers now. He will be giving a talk for our club. It will be over Zoom, or if you want to like come in person just to watch a Zoom talk, you can also do that. And then also next Monday, we have another talk from another cyber alum, Sanjna Sarda. It is Monday 6 to 8 p.m. in Kirchhoff 133. I believe she's doing a PhD at Stanford right now. Oh, she finished her PhD at Stanford. All right, neuro. Yeah, so she's working at neuro. She finished a PhD at Stanford. Very cool person. Also come check that out. And then PBR next week, Tuesday, we'll be doing a joint practice with like University of Washington CTF team. And then next Wednesday is, so basically like next week, this day, this time, this room, Benson will be giving his software verification talk. And Benson really wants you to come. Ooh. All right, so just like a very quick review, the stack, right? And also keep in mind that like the stack diagrams, the ones on the internet will always be like one of two orientations, which are complete opposites, right? So the one that Ryman uses is like the low addresses are on the bottom and the high addresses are on the top. And like, I'll try to keep things consistent like this. I think there's like one diagram that's very explicitly labeled that's not like this, but just keep in mind, right? Most of the diagrams will be low on the top, bottom, high on the top. The stack is a like last in, first out data structure. So like whatever you push last will be popped first. And it grows downwards. So like the stack pointer RSP, which points to the top of the stack, will have the lowest address. And like RBP, which is the base of the stack, which isn't always used, but is very frequently used, will have the highest address. And by manipulating RSP, you can like grow and shrink the stack. So like if you subtract from RSP, that means you are growing the stack because it grows downwards. If you add to RSP, then you are like shrinking the stack. And like in x86, how the stack is organized is basically when you like use the call instruction, it will push the return address onto the stack, right? And then a lot of functions also have what's known as a stack frame. So they will like, you know, basically allocate a new chunk on the stack for themselves. And creating this stack frame will frequently involve pushing like the old RBP value. So RBP is a base pointer, right? They'll push the old base pointer and they'll set a new one. So like you will see this diagram doesn't have it. Oh, actually this diagram does have it right here, right? RBP might be pushed here right below the return address. And then like below the return address and RBP, then the local variables will be placed. And this allows you to like have recursion as well as like procedure calls, right? Because like you can actually have every function have a separate stack space instead of like overlapping them. The idea of like buffer overflows that we covered in class is that like you want to overwrite the return address, right? Because you'll notice like on this diagram, the local variables are in lower memory than the return address, right? And like buffers grow upwards. So if you read in data to like the local variables and you like read in so much data that it like overflows the buffer that was allocated for it, then you'll end up reading into the return address. right? So you can see here, like this is an example function, right? We're allocating space for the stack with this subtract. And then we are like reading our data. In this case, it's a bunch of lowercase a's, and lowercase a is 6.1 in hex, right? And you will notice that our data, we allocated 16 bytes for the buffer, but we inputted 32 bytes. So what happens is the a's overflow into our original RBP and then our return address, right? And then basically, like as our function executes to the ret, it will then try to return to like hex 616161 whatever, because that's like what overwrote the return address. And so you do have to watch out for like little endian a bit, because you might think like if you do like A, B, C, D, which is 61, 62, 63, 64, right? That is not actually the address 0x61626364, right? Because in little endian, it's reversed. So actually be 64, 63, 62, 61. So you want to like sort of enter in all of your addresses like in reverse. And then in the chat, someone asked why A specifically. It's just for demonstration purposes, because it's really obvious when you see a bunch of like, basically I have it memorized that like lowercase a is 6.1, right? So if you enter a bunch of A's, it's like really obvious to see in the memory dump when you just see this wall of like 6.1 that's your input. And this is like another example, right? So like you can see over here, there's another example, right? If you enter 1, 2, 3, 4, 5, 6, 7, 8, which is like 3, 1, 3, 2, all the way to 3, 8, the address will start with 3, 8 as the most significant byte. And now we're gonna cover something known as code injection. So to cover what code injection is, we have to first like cover some like background information on like how x86 execution works. So every region of memory has permissions just like files. And this is kind of weird to think about, right? But you have to understand, right? Like with an 64-bit system, addresses are 8 bytes. So there are like 2 to the 64 like addressable bytes of memory. And there is like, that's a huge number. Your system obviously does not have that much RAM, right? So only like small regions of these memory are actually mapped to physical memory. And each one of these mappings has like a read permission. So if that's set, then you're allowed to read from the memory. A write permission, which like allows you to write to the memory, and an execute permission, which lets you actually like call it as code, right? So if a region of memory is both writable and executable, that means you can write code to it and then you can execute it, right? So you can just like write raw machine code and then jump to it, and then, you know, like your code will be called. And this is commonly known as shellcode, because most of the time you just put code that gives you a shell in there. And so also due to how input is read, shellcode generally should avoid new lines. So new line is like hex 0A, right? And so a lot of the time buffer overflows happen with functions like fgets or scanf, which will read input until it encounters a new line, right? So if your shellcode has a new line in the middle of it, it will frequently not be read correctly, which is why like, you know, all of the shellcode you find online will like do anything to avoid having a new line character. And this is also why like CS33 sent out an email saying like, if any of your addresses have 0A in it, like email us for a new bomb. It's because that's a new line. If you try to enter it, it'll just stop reading input. And so this is sort of a diagram of like how to jump to your injected shellcode, right? So you have like your buffer here and the return address is up there. So you just make like the first part of your input be like actual shellcode, right? And then you just write like the address to your input as a return address. This like involves like being able to know in advance the address that your input will be read into, which if it's not randomized, then you can just go into GDB and you can like look at the address and then just insert that in there. So there's also like, if it is randomized, but like not that randomized, then there is this technique known as NOP sledding. So basically, hex 90 is the opcode encoding for NOP. And NOP is an instruction that does nothing. It just moves on to the next instruction. So this is very convenient because it allows you to basically extend the length of your shellcode. And anywhere in this NOP sled, if you jump, it will be valid, right? Because it'll just run through the NOPs until it reaches your actual shellcode. So this allows you to increase the size of your input to actually increase the chance of guessing correctly. You probably won't need to do this though, because on modern 64-bit systems, there's a lot of randomization. You're almost certainly not going to be able to guess it. But this was very relevant for 32-bit systems, where there were 8 bits of randomization. So, or maybe it was 11. But it's some small number that was actually guessable. This is less important now. And then this is what reason is there to use ROP? We're getting there right now. So there is this very common exploit mitigation now named NX, which stands for no execute. It is also referred to as W XOR X, which means write XOR execute. It basically exists on all modern systems. If NX is set, which is the default, then there will be no writable and executable pages, which basically just stops code injection from working, right? But that doesn't mean that there can't be any writable and executable pages. It just means that the program doesn't start with any, right? So mmap is a Linux system call to map a new region of memory. You can still call mmap on a new page to make it writable and executable, or mprotect, which changes the permissions of an existing page, can be used to set an existing page to make it writable and executable. So if either of these happen, then code injection is back on the table. And then very quickly, we're gonna go over this library called pwntools. It's basically a Python library that is specialized for binary exploitation. The main thing is it can automate IO with the executable, right? So a lot of the time you may have to read in some input and then change your behavior based on that output, right? So this lets you script that. You can install it with pip install pwntools. I believe it also works on CSNet. And then here's just an example of doing IO with pwntools. So this is actually on the attack lab, but we're starting a process, right, with the process function that basically just runs a local executable. We're setting that to the variable p, and the next line we're calling p.receive until, and then cookie. So we're because the attack lab prints the cookie as the first thing, right? And now, the next line, we're reading in the cookie, right? So the cookie is printed as hex. So what we do is we receive the line, and then we strip it to get rid of the trailing new line, and then we decode it, because Python 3 is everything is bytes by default and not UTF-8. So we need to decode it from raw bytes into a Unicode string. And then we just call int on that with the second argument of 16 to read in a base 16 number. And then now we just have a print that prints our cookie, and then we can send 100 A's in a line or whatever. And then the last call, interactive, just returns control back to you. So it will pipe the standard output of the binary back to your terminal, and pipe your terminal standard input to the binary.
I thought in Python, when you send the byte string, it's weird because Python's UTF-8 encoded, and it's has random stuff attached to the end.
Pwntools. So if you print something, then that's weird. But pwntools send line will literally just send the raw bytes. It will not try to do any encoding. Okay. And you could send a non-byte string as well, and it will encode it into bytes. But I just prefer to use bytes everywhere because it's I don't know, less chance of error, I guess. And then another example, ELF loading. I'm gonna quickly skim over this. You can go back to the slides. The slides are posted in the Discord, and look at this code. But basically, you can also just load an ELF, which is the name of an executable on Linux, right? And then you can extract the addresses of functions using .sin in order to actually get the address of a function without having to open it in object dump, like copy paste the address. And then also this P64 function, very important. This is very useful. It packs a number as a 64-bit little endian long. So like you don't have to manually reverse the bytes yourself. It saves like a lot of headaches. And likewise, there's like a P32 for like 4-byte ints, and like a P16 and a P8, even though P8 is not very useful. And then also pwntools can assemble shellcode, right? Because normally you don't write in raw machine code because I don't know who has like x86 encoding memorized, but not me. You like writing in assembly. So pwntools has a function called like ASM, which will like compile assembly into machine code. First, you need to run context.arch equals AMD64 to set it to 64-bit because it defaults to 32-bit. But you can just like give assembly and it'll compile it to shellcode. Note that pwntools is using Intel syntax, and like every single tool online is also using Intel syntax, and there's no way to configure it. But Intel syntax, basically you just reverse the argument order. You don't put percents or dollar signs, and like the memory dereference syntax is like actually normal. But yeah, you can just apply assembly. And I also use the ljust function here. The ljust will just like pad it to a certain length with spaces, since a lot of the time you want your input to be a certain length, right? Because you might want to like align the overwrite to the return address or whatever. But you don't really know how long the shellcode is going to be. So like this just says like however long it is, add however many like spaces you need in order to like pad it to that length. And you can also provide like a second argument with the padding character, but that's not really relevant. And I guess we're gonna do a quick demo now on like how to actually exploit a program. So it's like this. You can see this, right? Yeah. All right. We're gonna check the C source code here. You can see we have like a win function, right? And this win function, like it has an argument and it has a magic number, right? And if like both of these are like a certain value that you have to control, then it'll say like it's correct, and then it'll like print the flag for you. And then in main, we have like this thing, right? Which it looks very daunting, but like we can break it down, right? I guess I could sit in the chair. Wait, but that can't. That's sit here. So I guess we can just like break this down a bit, right? So first, what's happening is this is being M-mapped. So remember that mmap is like a syscall to memory map a new region of memory. This is the address that it's mapped at. So like this will always be at this address, right? If we like run it, you'll see it's always at this like 1337 address. And then like the next argument, this like hex 1000 is the length, and then these are the permissions. Note how it's both writable and executable. So that's like, you know, it might be vulnerable to code injection. And then like this is just like other mmap flags that you don't need to worry about. It prints some addresses. You don't need this, but it's just like there to help you. And then it lets you input, you know, like this many bytes into the writable and executable memory. So you can write like whatever code you want. And then it defines like a buffer on the stack, right? And then it reads into the buffer. But you notice this is in hex and this is not. So this buffer is like 64 bytes. The read is like over 100. So it overflows by a lot. And if we like go into GDB and then we disassemble the, what is it, like main function, you can see at the bottom, this is the overflowing fgets, right? Oh, this is like kind of hard to see. Not great contrast. But the like first argument to fgets, which is the buffer, is RBP minus 0x50. So if you remember the stack diagram from before, RBP points to right before the saved RBP, and there is a saved RBP because of this. But actually, I guess you can even test with debugging, right? Like if we break at this address and we run and then we like input whatever here, right? We can see the first argument, which is in RDI, or I could like even like print RDI. The first argument, which is in RDI, is like this address. And if we like take a look at the stack, or actually I'll just do info frame. So info frame basically like tells you where the saved return address is, which is at this address, right? So it's like this offset from the start of the buffer, hex 58. And you can compute this because like if you look at the assembly, it reads into like minus hex 50, right? So it's at, you first need to like write hex 50 bytes to fill the buffer, and then the saved RBP, which will be popped by the leave instruction, is another 8 bytes. So that's where you get hex 58 from. So like this many, and then it's your return address. And where do we want to return? We want to return to where our injected code is, right? So like wherever this is. So basically in here, we want to write some code, and then like in the overflow, we want to jump to it. So for now, what we're going to do is we're going to like, we're going to make a new Python script. We're going to import pwntools. We're going to like start the process. And just to like make sure it's working, we'll just call interactive immediately. And you'll see like, you know, it's working, right? It's running. So I guess what? Did someone say something? Oh, okay. I guess the first thing to do is like we can
check your mic. Is it working?
I think it should be working. I don't know why it doesn't show green, but like Chris could say he could hear me, so
Okay, yeah. Now it's working, it looks like.
Oh, Jason leaves also in the chat. Incredible. Yeah. Okay, so the first thing we'll do is like we'll just send like a bunch of A's, right? For like this is the first input is our like injected code, and the second input is like our actual overflow. So remember our offset was like hex 58. Chris is never gonna stop. And then we will just like use P64 to like pack a 64-bit little endian number, and then we'll say like something that is very recognizable, just this like increasing sequence of numbers. And before that, we will like attach GDB to it so that like we can actually. pwntools has another very convenient feature. You can just like attach GDB to a process, right? So we can actually look at it. This is so small. So we want to like see where the return in main is jumping to, right? So we will like break here on the return. We will continue. And you can see it says cannot disassemble from PC. PC refers to like the RIP. Because it's like if we take a look at what's on top of the stack, it's this, right? So return will try to pop this into the return address, which like obviously will not work. It's segfaulted, right? Because RIP is like there's no valid memory there. So now what we can try to do is we can try to actually jump to our injected code, right? That was the goal. Like we made sure that we got the offset correct. Now we just need to like control it. So this is the address we want, right? So instead of this, we will do this. And if we like set a breakpoint again and continue, you can see we are now like jumping. If we step, we are now jumping into our injected code. So now we should probably like inject some actual code that, you know, gives us the flag. So the first goal is to just call the win function, right? Because the win function will print the flag. Let's not worry about like getting the argument correct. Let's just call the win function. So you'll notice like the win function, right? Like it just takes an argument, it prints stuff. So let's just get the address of it. I guess I'll do the automatic approach because it's cool. So we'll load the ELF with pwntools, and then in our injected code, we will use ASM instead. And something to note about like the x86 call instruction is it's actually like relative. So it's very, very non-trivial to like call an address with an immediate as an argument. So what we're gonna do is we're gonna cheat a little bit. We're going to move the address into RAX. And actually, you know what? We'll just do the object dump route. This is fine. The win function, and we'll just copy like the address. So this is the address of win, right? That is true. No, because I deleted the line. All right. So what we're gonna do is we're just gonna move like the address into a register, and we're gonna call the register. And in AT&T syntax, this would be like move like dollar like, or this should also be like move Q, and then this should be like called. This is like what's in this comment is like the equivalent in AT&T syntax, or I'll put it in a string so it's like easier to see. This is like the AT&T syntax, but Intel syntax just reverse the arguments, right? And like get rid of the like suffixes. Whatever. Good enough, right? This is like the AT&T syntax. So hypothetically, if we just run this like without GDB, we should see like the win function gets called, right? Yeah, this incorrect is from the win function. So now we just need to manipulate this magic number as well as the argument. The argument is pretty easy, right? Because if you remember, the first argument is always stored in what register? RDI. Yes, RDI. So we will just move. What was the value? 1, 2, 3, 4, 5, 6, 7, 8. Okay. We will just move like this into RDI, right? And now if we run it, you will see the argument is correct. So now we just need to like set the magic to be correct. And to do that, what we can do is just like I'll do another thing where I just like move the address into a register because it's easier that way. And the address I will just get in GDB. So this is the address of like the magic number, right? So we will copy that. We'll put that into here. We'll move it into RSI. Why not? It doesn't really matter where you move it. So RSI now has the address, right? And I will move into this is like we'll move into RSI. Actually, would it be clearer if I like just split this onto multiple lines? This would probably be easier to see. All right. By the way, the triple quotes is just like the Python syntax for a multi-line string. It's like you can split onto multiple lines. So this is like the equivalent of this in like AT&T syntax is like move, what is it? Move L, and then like what is the number? It's like this. So this is like is there a percent? There is a percent, right?
Yeah.
Yeah. So like this is the AT&T version of this, right? And so this should like properly move it into magic. Yeah, and it prints out the flag because we successfully caught it. And we can like check in GDB that this works, right? So in like main, we'll break here. We'll continue, right? So you see, like at the top of the stack is that address to the like injected code that we inputted, right? And then we can step through. We're now in our injected code, and we see like this is the code we injected, right? So we're moving this into RAX, and if you scroll up, you can see like RAX now has the address to the win function, right? We're moving this into RDI, so RDI now has like what we want. And then we're moving this address into RSI, right? Where is it? Yeah, RSI now has like the address to magic, right? And now we're like moving this, like we're moving the value into magic. And if we just like print what's in magic, you see it's like 1337, 1337, right? And then we're calling RAX, right? Which is like the address to win. And like now we're in the win function, everything's correct, and it'll like print the flag. So that is like sort of how to do an exploit in full using pwntools. And keep in mind, right, you did not have to use pwntools here, right? Like this is just like static input, right? You could assemble this yourself by hand, right? Like I could probably go onto like, there's another site like ASREPL. This like is an online assembler. Like I could copy paste all of these individually and like copy the hex, right? And like input all of this myself manually. But it's a lot more effort to do that, and it's a lot easier to just like do it with pwntools, right? You're still doing the exploit like yourself, but it's just, you know, less effort. And now back to the presentation. There is one more thing. So
I think Ryman, this isn't like really the best way, but he has like something in the spec about how you can get the opcodes right. You like type the assembly and you can compile it and then like decompile it.
oh my god, manually invoking an assembler is so cringe. It's
Yeah, that is how Ryman like
when you
says
had
to
like
do
the
it.
assembly before,
in pwntools?
you can just like do it in multi-lines. You can just use new lines instead of semicolons.
Yeah, like because pwntools uses like internally it uses like GNU assembler. So like GNU assembler it like recognizes both semicolons and new lines as like separators. So either works. So you know that's all like cool, but no modern system will have a page that's writable and executable. So you know, injecting your own code won't really work. So there's this question of like, how do you actually get code execution then, right? And there's this big thing where the program code is in an executable page, right? So if we could just use the code that's already in the program, then we don't have to inject our own code. And this is where the idea of ROP chaining comes into play, right? So ROP chaining utilizes the pre-existing code in the program in order to get execution, which means you don't need a writable and executable page. So this essentially bypasses NX. So you know, if you overwrite like just a return address, then you can do one jump, right? But what if you chain together multiple things? So we do this by utilizing gadgets, which are basically just like, you know, small sets of opcodes that are already in the program. And it's very important that gadgets end with a ret instruction, because what the ret will do is it will jump to the next gadget, right? So you imagine this code is executing, right? This like a pointer to the pop RDI ret gadget will be first on the stack, right? And it'll return to this gadget, right? So now the stack pointer points to this number, right? And then the gadget will execute pop RDI, so it'll put this number into RDI, right? And keep in mind, this is part of your input. So now using this gadget, you're like, you can control a register's value using just your input. So you can pop this into RDI. Now the stack pointer is pointing here. to your address of like some other function. And then the ret instruction in the gadget will now pop this address and return to it. So you've essentially like chained together two different addresses in order to simulate like a function call with an argument. So like that's sort of the power of ROP gadgets. And it isn't restricted to just like pop RDI ret, right? You can use like any gadget. Ideally it ends in a ret because it's like very hard to use otherwise. But like this lets you sort of like chain together like different amounts of code. And like finding gadgets is a little bit hard. First of all, they have to be in an executable segment. So basically like the program code itself. Don't know the address. You can't really supply it. So yeah, it's usually for these reasons, it's usually located in the program code itself. And this is a very important thing. It can be inside another instruction, right? x86 does not have any concept of instruction alignment, right? Like if you jump to an address, it will just interpret whatever is there as an instruction. So like in this example, right, like the move AX like 0xC35F instruction, right? It's encoded into like 66B8 5FC3, right? Like these 4 bytes represent the move instruction. But if you just jump to these last 2 bytes happen to coincide with the encoding of pop RDI ret. So this is where a lot of gadgets actually end up getting created, right? Because in real code, you would never see pop RDI ret, right? Like why would you pop into a clobbered register right before returning from the function? Like that's so counterproductive, right? But if there just happens to be literally any instruction in the entire program with this, like these 2 bytes in the encoding, then you can create a pop RDI ret from it. And so like to actually find these, you kind of, there's scripts that I'm not gonna go over because I don't know if that's adhering to academic integrity. The sort of like do-it-yourself way is to literally, like in every single instruction, if you see like a C3, which is the encoding for ret, then you just like copy like different amounts of bytes before the C3 and disassemble it and see if it's a usable gadget. So like in this case, you would see the C3, you would like try 5FC3, you would see that's pop RDI ret, and you'd be like, oh cool, I found a gadget. And then we're gonna quickly cover another like, what? Wait, I did not use any command earlier to list ROP gadgets. That never happened. So we're gonna cover like another mitigation called ASLR, and this stands for Address Space Layout Randomization. This is kernel level, so like it will not be disabled, right? Because no one wants to like go into their kernel settings and like disable it just for like some challenge, right? This will be enabled. The stack, heap, and libraries like libc, which is the C standard library, will all be put at random base addresses. So this means that you don't really know where like any address is because it's randomized every single run. So like if you're like reading input into a buffer on the stack, it will be at a different address every single time you run the program. And it's like basically impossible to guess because on 64-bit systems, it's like over 30 bits of randomization, which means there's like a 1 in 4 billion chance of you guessing correctly. In 32-bit systems, it's a lot less, which is why not sledding is actually viable, right? Because you can make your input big enough where you can actually just guess where it is. And then if pi is enabled, pi stands for position independent executable, then the code and data segments of the executable will also be randomized, which makes ROP chaining even harder because if the code is randomized, then you don't actually know the addresses of any gadgets. And this means that you will have to get what is known like in the Pwn community as a leak, basically like, some way to like print out a pointer, and using that pointer, right? Since like it's only the base address that's randomized, everything else will be at like a constant relative offset to that base address. So once you leak like one pointer for the segment, you can figure out where everything else in that segment is. But keep in mind that like these things have separate bases. So leaking a stack address will only tell you where things on the stack are, right? Heap will be at like a different offset, and you will need like a separate heap leak if you want to like, know where those are. But for now, you won't really have to worry about leaks because this is more advanced stuff and like there's no pi on like any of the binaries. And then a useful tool, I like showed this in the demo, ASREPL.johnpalmisk.com. It lets you assemble and disassemble x86. So you can see like if I enter hex bytes, then it'll like give me the disassembly. If I like enter in an instruction, it'll give me the hex. And so this is very useful for finding gadgets, right? Because you look at the opcodes and like object dump, and you like monkey C3 neuron activate copy paste, see if it's like useful. And now, like, useful Jeff commands. So again, Jeff is like an extension to GDB. If you don't have it installed, I think it's like, it's super, super helpful to have it installed, right? Just like search up like Jeff GDB on Google and like just install it. It makes your life 10 times easier. And it's like super, like it's so good for visualizing the execution of your program. And Jeff also has some like very useful utility commands. The first one being VM map. This stands for like virtual memory map, and it will like list every single memory region and the permissions on them, right? And so you see like, this memory region is from like 606000 to like this address, and the permissions is read and write, and it's also labeled as a heap, right? And this region right below it, it's a bit hard to see. This is read, write, execute. So that's like a big red flag, right? That means that, you might be able to like inject code into that page, right? So I highly recommend just like, like whenever you're like exploiting a new target, just like run it, right? In Jeff, run VM map to like look at the memory pages and see if anything is like, abnormal like that. And then Jeff also has a checksec command, which stands for like check security. I don't know. It lists like the common mitigations, and then it like tells you if they're enabled or not. So right, like this binary, I run checksec. There is no stack canary, right? If there is a stack canary, then stack overflows become much harder, or buffer overflows, I guess. Alex is like staring me down because it said stack overflow.
I didn't even notice that.
Right, NX is enabled, which means that like by default there won't be a writable and executable page. Pi is disabled, very good. And then don't worry about Fortify and Railroad. Those are like more advanced stuff that isn't relevant right now. Also, again, ASLR is kernel level, so it won't be listed here. Just assume it's always enabled. Although GDB by default like disables ASLR for binaries run in GDB, but like, that's not, if you run it outside GDB, ASLR will be enabled again. And you can like turn on ASLR for debugging with like the ASLR on command, but you don't need to worry about that. And this is like a normal GDB command. It's not a Jeff thing. Info frame, it tells you like info about the current stack frame. So this thing, very important. It tells you where the like return address is saved, right? This address, if you inspect it, you will see this is the return address. So like this will let you know where the saved return address of the current stack frame is. Jeff also has a very nice command called dref. Dref is basically like the X command but prettier, right? So you'll see when I run like dref -L20, the -L20 just means like output 20 like groups of 8 bytes. And it defaults to like the stack, but you can like provide it another argument for the address, right? So this dref command, it groups everything into 8 bytes, right? And it color codes it. So red addresses mean that they're pointers to the code segment. I think like purple addresses are like pointers to the heap. No, purple is stack. Green is heap. Anyway, there's a color code somewhere, but like basically it color codes all of the pointers, right? And if it's a string, it'll try to like represent it as a string. If it's a pointer, it'll like dereference it and tell you like where it's pointing to. So this is like very helpful for like getting information very quickly. It's also good for like inspecting your ROP chains. And then like that is about it for the presentation. As always, if you like want to work on challenges, I have created 4 challenges for today's meeting. At there, it's not on this. I'll just make a new slide right now. No, don't autocorrect it. Where's the link button?
Just put HTTPS in front of it and enter. Enter. Yeah.
All right. There are some challenges for the meeting. You don't have to do these. You can work on other stuff, and we'll help you with the attack lab.
Challenges here because I don't see them.
It's binary exploitation. Oh, I didn't deploy them. I should do that. And then that is about it.